Lecture 9. Digital Sensors. Introduction 1. As we have seen, the remote sensing techniques serve to know and measure some of the characteristics of surfaces and bodies far away from the observer, without direct contact with it, exploiting the electromagnetic energy, emitted, reflected or transmitted, as a vehicle of transport of data. This data, which regards fundamental parameters such as reflectivity, emissivity and transmissivity, is acquired by special measuring instruments that can be of various types and classified in various ways. Thus we find instruments that passively measure the energy coming from the observed surfaces, either spontaneously emitted or reflected or transmitted as a part of that coming from another external source, such as the sun. Other measurement systems, on the other hand, are called active when the energy source is inherent in the instrument itself. For example, a camera that works with the flash is an example of an active tool, as it has the device to illuminate the subject, of which it acquires the reflectance. An important tool for active remote sensing is the radar, since it has the energy necessary to illuminate the scene to be observed, sent by the same antenna which then receives the return information. Introduction 2. The instruments can also be classified in another way, that is distinguishing between instruments producing measures, non-imaging sensors, where the measurement is acquired in the form of a number or a signal, and imaging sensors in which the final data is a two-dimensional representation of the scene taken. Sensors. 1. By sensor we mean any device capable of detecting and then recording the electromagnetic energy coming from a scene and capable of converting this energy into useful data for subsequent analysis, in the form of an electrical signal or other. In this sense, for example, the eye in living beings can be understood as a sensor, as well as the very common photographic camera. In optical systems, the electromagnetic energy is conveyed by the optical center of the system to a detector, which transduces the incident power in a photochemical effect or in electric voltage. Sensors. 2. Optical sensors include some common structural parts such as an optical part, which serves to convey the radiance onto the detector. The spatial resolution limit, the acquisition geometry, the optical characteristics and the maximum energy available to the detector sensor depend on it. A set of spectral filters, physical or otherwise, which determines the instrument's working bands and their amplitude, in practice the spectral resolution. The sensory part, intended as a detector, able to detect and transduce the radiance conveyed on it. The characteristics of the detector determine the radiometric resolution, whereby the physical input signal, usually a flux expressed in watts, is translated into a signal that can be managed as data, such as an electrical voltage or a photochemical reaction. This transformation will make the initial data useful for subsequent processing and/or visualization. The data recording media for storing the detected radiance value. Sensors. 3. In some systems, the first three parts are replaced by other types of electromagnetic energy conveyors detectors such as radar band antennas. Normally the acquisition phase lasts for a small interval of time, while the interest is above all on the spectral and spatial variations of the radiant flux, since these variations are then significant to understand the content of the scene. Since the radiant flux is measured in a small period of time, the physical quantity that is recorded is in fact energy. Usually the radiant flux or the radiant flux per square meter is used simply because it is more convenient and because integration over time is a function more of the sensitivity of the detector than of the measured quantity. It also generally arises that the integration interval over time remains constant, so that the differences from scene to scene are essentially due to changes in the effective radiant flux. CCD sensors. 1. These detectors are to be considered electrical. Despite this, given their current and future importance, they deserve particular attention. In fact, in the design of sensors for image acquisition, the most established technology involves the use of multiple detectors in line, detector array, structured in such a way that each of them accumulates a charge which is then stored, downloaded and translated into signal from a special system called CCD, charge-coupled device. Every single CCD behaves as if it were a capacitor in which the photons incident on an armature produce an electric charge, or better a potential niche, in the underlying reinforcement. This charge is then read and transferred as an analog signal to an electrical circuit and is the measure of the amount of light, or photons, entering the device, following figure. The series of impulses, like a chain of buckets of water during a fire, is transferred to the circuit in a sequential manner by means of a position register, shift register. The signal is then translated and recorded in digital form, and the succession of the different arrivals goes to recompose the initial line. Sensors calibration. 1. An absolutely not negligible aspect that concerns the measuring instruments, and therefore also the sensors, is the ability to guarantee measures that can be compared over time, that is, measurements that have absolute values and stable calibration references, with equal constancy of instrumental functioning. This refers to the three fundamental characteristics of the data: geometric, spectral, and radiometric. By geometric calibration we mean the need for internal coherence between the structure of the elements that make up the image, cell, and the maintenance of the projective correctness of the image with respect to the scene taken. It is a typical problem of photogrammetry. Sensors calibration. 2. The problem of spectral calibration arises instead mainly in multi- or hyperspectral sensors, where the spectral information detected sometimes does not correspond exactly to that corresponding to the ground because it is affected by the influence of the surrounding cells. In addition to problems connected with the different design of the systems, the spectral correctness of the survey is directly linked to the geometrical one. The interventions for this type of calibration require rather frequent and distributed, ground truth, ground reflectivity measurements, as well as the application of procedures linked to the values present in the image itself, in image calibration. The radiometric calibration of a sensor, whether carried out inside the instrument or through external references during data acquisition and in the laboratory with respect to standard sources, is fundamental in order to correlate the observed signal to the effective radiance L that reaches the sensor. Sensors calibration. 3. The general criterion consists in the fact that the signal produced by the sensor is always compared with a standard radiance source taken as a reference, whether included within the instrument or external. The incoming signal S is usually calibrated with respect to light sample sources at known frequency and intensity, very stable over time. In the hypothesis of detectors with a linear response in electrical voltage, as a function of the incident radiance L, a simple calibration of the response function expressed in terms of digital numbers dn can be performed by means of the simple slope and the intercept of a linear function. In these cases, the mathematical calibration function has the following expression: dn equals gl plus b, where dn equals digital number, g equals gain or amplification of the system, L equals spectral radiance incident to the detector, B equals offset value, residual signal when L equals 0. The numerical values dn found on the digital images can therefore provide the values of the original radiance of L recovery with the use of the following equation: if the lower and upper limits, Lmin and Lmax, of the dynamic range of each band are known, where L equals spectral radiance, Lmin equals spectral radiance when dn equals 0, instrumental calibration data. Lmax equals spectral radiance when dn equals dnmax. dnmax equals dn maximum radiance value, 255 for 8-bit conversion. dn equals digital number value in a generic image cell. Signal sampling. The radiance coming from the target is suitably sampled to convert the analog signal into a digital one. Diagram of the sampling process and discretization of a signal. Analog starting signal is read at regular time intervals, sampling operation, and returned in discrete quantities. The more samplings over time, the more the discrete signal resembles the original analog one. Passive systems. This group of systems are designed to detect the electromagnetic energy reflected or emitted by the target, being the target illuminated by the sun. These are instruments that, excluding radiometers operating in the microwave region, have in common the need for an optical part, be it refraction or reflection, to make the radiance detected on the focal plane of the system, central perspective. Based on their operating characteristics and technological development, different types of instruments can be distinguished: digital photographic systems, radiometers and spectroradiometers, optical electronic systems, and, finally, optical mechanical systems. In this discussion we will focus exclusively on optical mechanical and optical electronic systems. Scanning systems. 1. Acquisition devices normally take the name of scanners and are currently almost all digital. The exploration of a scene with a scanning technique is used when other systems show operating limits, both spectral, radiometric and geometric. These systems are able, through an ordered sequence of measures in space, to reproduce a two-dimensional scene, returning it in the form of an image, normally digital, according to a matrix of elementary cells that will then correspond to the cells of the image. The image matrix is created in various ways by a series of measurements made by the instruments that use scanning radiometers able to explore a scene, cell by cell, line by line or simultaneously, see figure below, combining the motion of the platform on which they are mounted with the transversal rotation of a mirror. When the rotating movement of the mirror is replaced by an oscillating movement, a scanned image is obtained with the advantage of a greater acquisition speed. Depending on how the measurements are made, there are basically two detection modes, called whiskbroom and pushbroom respectively. Whiskbroom scanners. 1. They are the first that have been developed and generally have the following configuration, whether they are mounted on airplanes or on satellites: a mirror inclined at 45 degrees with respect to the axis of motion of the vector, plane or satellite, kept in rotation at constant number of revolutions from a motor, diverting the radiations coming from the ground towards a main optical system for collecting the radiations. This optical system, generally with reflection, consists, like a Cassegrain telescope, of a main parabolic mirror which conveys the radiation towards a small divergent mirror which in turn sends it back, through a hole in the main dish, behind the system optical to strike the sensitive element of the system, detector or detector, in focus. The combination of the rotary motions of the rotating scanning and translational mirror of the vector allow the exploration of the ground in a sequential and ordered way through a series of contiguous strips, in appropriate and determined cases of speed-height ratio. All Landsat sensors prior to Landsat 8 use the whiskbroom design. The OLI instrument on Landsat 8 uses a pushbroom design. Whiskbroom scanners. 2. General scheme of a whiskbroom scanning device and relative ground exploration. IFOV stands for instantaneous field of view, that is the angle of geometric resolution of the scanner, not to be confused with the angle of view, which determines the total embracing on the ground, different depending on the relative altitude. Pushbroom scanners. 1. Pushbroom scanners, also sometimes referred to as along-track scanners, use a line of detectors arranged perpendicular to the flight direction of the spacecraft. As the spacecraft flies forward, the image is collected one line at a time, with all of the pixels in a line being measured simultaneously, figure below. A pushbroom scanner receives a stronger signal than a whiskbroom scanner because it looks at each pixel area for longer. One drawback of pushbroom sensors is that the detectors in the pushbroom can have varying sensitivity. If they are not perfectly calibrated, this can result in stripes in the data. Sensors that use the pushbroom design include Copernicus Constellation, SPOT, IRS, QuickBird, OrbView, and IKONOS. The advantages of a pushbroom system compared to a whiskey system are the following. Absence of moving parts, so total absence of vibrations. Absence of spatial sampling of the signal because in this case it is already discrete, even if not digital. Pushbroom scanners. 2. The disadvantages of a pushbroom system compared to a whiskbroom system are the following. Difficulty in constructing an array with all identical detectors. Need for periodic calibration of all detectors. Problems arise when one or more detectors stop working, a continuous line is produced on the image with no signal. Currently the technology moves in favor of pushbroom systems even if the whiskbroom systems continue to be operational in many cases, both on aerial and satellite platforms. The multispectral systems in this case are realized with a linear array for each band, as shown in the following figure. Matrix scanners. 1. When the detector line is in 2 dimensions, a matrix CCD system, or two-dimensional or framing array, is obtained, which acquires the image at once and the energy of each cell is recorded simultaneously over the whole scene. This structure is typical of digital cameras and cameras that have definitely replaced the use of previous analog systems. Inline CCD detectors offer the great advantage of collecting data relating to multiple lines or different spectral levels simultaneously, allowing the single sensitive element to hold the charge longer, thereby increasing the recording time and thus improving the ratio signal to noise. The system consists of a set of detectors, placed together to form a slab, a square or rectangular matrix, or aligned with each other in linear mode. In essence, each detector is the smallest photosensitive element that reacts in the presence of light, generating an electrical signal. During processing, each of these signals will be associated with a discrete value, represented in a two-dimensional form, which will be the image cell, thus reconstructing the matrix corresponding to the definitive digital image, which can be memorized and displayed through a monitor. Matrix scanners, 2. The principle of spectral operation of digital matrix sensors remains to be clarified. Let us examine the simplest case, namely that of a normal color image. As is known, any color of the scene contains in various percentages the blue, green, and red components of the light, so there will be a need for a sensor capable of measuring these components. In the vast majority of cases of digital cameras, this feature is obtained by having three types of CCD available, namely those sensitive to blue, those sensitive to green, and those sensitive to red. A bit like in the human eye, there are on the retina cones of type S, M, L, i.e. sensitive to the short, medium and long wavelengths of the visible spectrum respectively. The spectral selectivity of CCDs is given by a filter, or blue or green or red, interposed between the microlens and the CCD. Matrix scanners, 3. Enlargement of a CCD that actually forms a physical pixel of the corresponding numerical matrix. It can be seen how the interposed filter lets pass only one of the three fundamental components of visible light. Acquisition basics, 1. Scheme of the operation of a multispectral scanner. Since the incident radiation is divided into bands by appropriate filters, there are more detectors. In the figure, the same scanning line is seen simultaneously in 6 bands, thus allowing the creation of 6 images of the same area in different bands, as in the first version of Landsat's thematic mapper sensor. Acquisition basics, 2. As regards the geometry of the scan, and consequently the distortions present in the taken images, there are at least 4 considerations to be highlighted. Acquisition basics, 3. The first consideration is this: since the scanner IFOV is constant, the area intercepted on the ground is variable according to the shooting distance and the angle of view. This fact introduces a deformation in the final images, usually called panoramic deformation, which is then corrected at the software level. The second consideration is that, due to the panoramic deformation seen above, the ground strips do not occur with the same width, but with a minimum width at the nadir and maximum at the edges. There are therefore 2 choices in ground exploration, that is, or are kept adjacent to the edges or in the center. In the first case, information is lost; in the second case, we have redundant information. The normal choice is the second, then correcting the surplus of information at the software level. Acquisition basics, 4. The third consideration, valid above all in aerial shots, is that the platform is subjected to variations in attitude due to rotations around the 3 main axes, by convention called K, Phi and Omega, which correspond to yaw, pitch and roll. Since a scan shot is not instantaneous like a photograph, but develops over time, the geometry of the images may undergo deformations such as those illustrated in the following figure. These deformations are also correct when data is returned. The fourth consideration is related to the combined motion of rotation of the mirror and translation of the platform. The strips on the ground are not perpendicular to the flight axis, but are inclined. Moreover, since the tangential speed of ground exploration is given by d, where d is the observation distance, minimum at the nadir where it takes the value h, it is maximum at the edges and minimum at the center. The consequence is that the streaks on the ground follow a curve instead of a straight line. Acquisition basics, 5. The figure shows the distortions present on the image due to the panoramic distortion and to the effect of the variations of the 3 attitude angles, taken one at a time. It is clear that more than one effect is present in a perturbed atmosphere, and it is equally clear that in satellite acquisition, outside the troposphere, these distortions are minimal or absent. Acquisition basics, 6. Any object in space has 6 degrees of freedom, 3 Cartesian coordinates, x, y, z, and 3 angles of arrangement called by convention as phi, omega and k. They correspond, in aeronautical terms, to roll, to yaw or drift, to pitch or dive. Thermal scanners. 1. A special mention should be made of the scanner operating at thermal infrared. This type of scanning device in the following figure substantially does not differ from the scheme presented above except for two elements, namely, the presence of two temperature and emissivity surfaces unknown, acting as black calibration bodies, placed laterally with respect to the scanning mirror. In its rotation, the mirror sees these black bodies and sends calibrated radiation to the detector. In this way, the scan signal has two references and the quantitative use of a scanner in the strict sense is possible. The typical electrical signal resulting from an entire rotation of the mirror is illustrated in the following figure. The detectors in normal practice work on two classic bands, that is from 3 to 5 microns and from 8 to 14 microns, because in those regions the atmosphere is particularly transparent. Thermal scanners. 2. Landsat 8 TIRS optical diagram. The SSM mirror rotates between the nadir viewport, blackbody and deep space viewport to provide calibration at least once an orbit. Thermal scanners. 3. The fundamental characteristics of a thermal scanner, sensor that collects energy in the TIR, are two, namely the geometric and thermal resolution, which are in competition with one another. To give an idea, with 2.5 milliradians of geometric resolution, IFOV equals instantaneous field of view, instant by instant. From 1,000 meters of altitude we observe an area of 2.5 by 2.5 square meters, and it is possible to have a thermal resolution of 0.1 degrees C, that is to distinguish cells that differ from each other at least 1/10 of a centigrade degree, while with a geometric resolution of 1.7 milliradians the thermal resolution drops 0.2 degrees C.